only have to remember these 6 points for solving any question related to electric flux. Okay, so the area multiplied by the normal vector to the surface. Okay, so this is the electric flux through the curved surface minus E pi r squared. Similarly, we have the electric
Consider
flux.
the vertical component.
See, this vertical component is not required. So this vertical component k lambda by r that happens to be a part of a cylinder. So we are finding the area of that part of the cylinder, and that is the only calculation here. Alright, so let us discuss electric flux. So what is meant by electric flux? See, this electric flux can be roughly defined as the number of electric field lines passing through a surface. The number of electric field lines crossing an area can be called electric flux. This is only a vague definition. This does not reveal much about electric flux because physically there is no such thing as electric field lines. We can't see these electric field lines. Then how will you count them? So this definition is only a vague definition. So to understand the concept of electric flux, let us take this analogy. It's raining here. Now we want to collect some rainwater. So what shall we do? So we keep a vessel to collect some rainwater. So this amount of water collected by this vessel is analogous to the electric flux. See, this is not a perfect analogy, but this will help us understand the concept in a better way. See, we keep a vessel to collect some rainwater. So the amount of rainwater collected by this vessel is compared to the electric flux. Do you understand? Okay. Now tell me, what are the factors on which this amount of water collected by this vessel depends?
The intensity of rain.
Yes, the intensity of the rain, right? The heavier the rain is, more water can be collected. So one of the factors on which this quantity of water depends is this intensity of rain. Alright, yes. Is there any other factor on which this quantity depends? See, suppose you want to collect more water in a very short duration of time. So what shall we do?
Use a bigger vessel.
A bigger vessel, something like this. See, this bigger vessel will collect more water in a long period of time. But we want to collect more water in a very short duration. So what shall we do? Not exactly a bigger vessel, but a vessel with a wider opening. Do you understand? So the surface area that is exposed to the rain, so that should be more. That is when we get more water, right? In a very short duration of time. So the surface area is what matters, not the volume. Do you understand? So the area is one factor on which the amount of water collected depends. Do you understand? So this is one of the factors. So the intensity of the rain and also the surface area. Do you understand? So these are the two factors on which the amount of water collected by this vessel depends. There is also one more factor on which this amount of water depends. So that is, see, suppose we have the same vessel, okay, now same intensity of rain, but you keep the vessel not flat like this, okay, in a vertical position. Now you tell me how much water will be collected?
0.
Yes, no water is collected in this case, even though the intensity of the rain remains same and also the surface area of the vessel is same as the last case, but still the answer here is 0. So that means the angle also matters, right? The angle between the surface and the direction of raindrops, so that also matters here. If you keep the surface flat like this, that is when it collects maximum amount of water, which means when the surface is perpendicular to the direction of raindrops, we will get more maximum amount of water. When you keep it parallel like this, so no water is collected, so 0. So it can be anywhere between them, alright? Yes. So this scenario can be compared to the electric flux. See, we have electric field lines instead of the rain, and also we have a surface instead of that vessel. So the amount of water collected here can be compared to the electric flux through that surface. Do you understand? So that means this electric flux depends on the intensity of the electric field, just like the intensity of the rain here, and also the area of the surface and the angle between the surface and the direction of the electric field. Do you understand? So these are the three factors which the electric flux depends on. Do you understand? See, this gives you a rough idea of what an electric flux is. Do you understand? This is only a rough idea. Now we will define properly what an electric flux is. I'll give you about 5 or 6 points about electric flux. 6 simple points about electric flux. We only have to remember these 6 points for solving any question related to electric flux. Okay, now the first point here is, this is not the most general case of electric flux, it is only a particular case when the electric field is perpendicular to the surface. So this case is very important because in most of the cases you will come across situations like this when the electric field is perpendicular to the surface. So this case is very important, that is why we have taken this up separately before the most general formula. So when the electric field is perpendicular to the surface, then the electric flux is defined as this. So the electric flux is denoted by this symbol phi. Okay, phi is the symbol we use to denote the electric flux. So this phi electric flux is defined as the electric field strength, that is E. So E is the strength of the electric field, that multiplied by the area of the surface. Okay, this multiplied by the area of the surface. That's all. So this is the simple formula for electric flux only in this case. Which case? When the electric field is perpendicular to the surface. Like we have already discussed, the flux will be maximum only when the electric field is perpendicular to the surface. So that case we have electric flux having this formula. Do you understand? So phi equals the electric field multiplied by the area of the surface. Do you understand? So this is the formula that you have to remember for this particular case when the electric field is perpendicular to the surface. Do you understand? Okay. So this is one of the cases of electric flux when the electric field is perpendicular to the surface. Okay. Similarly, this is also a particular case, but this time the electric field is parallel to the surface, right? In that case, we have already seen what is the electric flux. When the surface is parallel to the electric field lines, in that case, the electric flux is 0. You understand, we have seen example also. So the electric flux is 0 when the surface is parallel to the electric field lines. That's all. So this is the second case. So these two particular cases are important. So the moment you see electric field lines parallel to the surface, so directly we can write the answer without using any other formula. So similarly, when the electric field lines are perpendicular to the surface, in that case we can use the previous formula, which is the electric field multiplied by the area. Alright, so these two particular cases are important, but the next one that we are going to define, so that is the most general formula. Okay, so that goes something like this. So this is the most general case of electric flux where the electric field is neither parallel to the surface nor perpendicular to the surface. In this case, what is the electric flux? Okay, so let us find a formula for the electric flux in this case. So electric flux. So here the surface is not perpendicular to the electric field. Alright, so what is the formula? So the flux here is equal to the electric field strength multiplied by the area. So E multiplied by area, that is only when the surface is perpendicular to the electric field. Okay, but here it is not the case. So what we have to do is, instead of multiplying E by the area of the surface, here we will take the projection of this area in the perpendicular direction, because we want to use the formula E multiplied by area, but we cannot use it here because so this area is not perpendicular. So what you do, you take the projection of this area in the perpendicular direction. Do you understand? So projection of area in the perpendicular direction, so that should be used here instead of the area of this surface itself. Do you understand? So E multiplied by the projection of this area in the perpendicular direction. The projection of this area in the perpendicular direction. Do you understand? So that's also, that is the formula. So not simply the area of the given surface, but you take the projection of this area in the perpendicular direction, because once you take the projection, now area becomes perpendicular to the electric field lines. Then we can directly use the formula E multiplied by the area. So that is the formula we've used here. See, this is not the proper formula. Okay, the formula we are going to derive, but before that, so this is also important, because sometimes instead of using the formula, we use this idea. So this idea is important. E multiplied by the area projection in the perpendicular direction. Do you understand? So this is also important. Is that okay? Yes. Now we will derive the formula. So phi equals, so E multiplied by, what is the projection of this area? Let us take the angle made by this surface with the vertical to be theta. Okay, with the vertical, that is theta. Now we have to take the projection of this surface in the perpendicular direction. See, we can either take the projection of area in the perpendicular direction, or you take the projection of the electric field in the perpendicular direction to the surface. Anything, right? Projection of the area or projection of the electric field, but we want the electric field and the area to be perpendicular. You take the projection of area or you take the projection of electric field, so it doesn't matter. So let us take the projection of area only here. So E multiplied by, what is the projection of something in the direction perpendicular, but it makes angle theta with the vertical. That means the projection of that is simply that area multiplied by cos theta, right? So that is the projection formula, right? So multiply by cos theta, because the angle with the vertical is theta, so the vertical projection is cos theta multiplied by that value. Do you understand? So that's all. So this is the formula for the electric flux. Do you understand? So E multiplied by A cos theta. So this cos theta will not be there if this surface is already perpendicular to the electric field. But here it is not perpendicular, so this extra term, right, cos theta is also to be used. Alright, done. Okay. Now if you observe, this looks like a familiar expression E multiplied by A cos theta. Doesn't it look like a familiar expression E A cos theta? So this can also be written as E vector, right? E vector dot A vector. You understand? This is the definition of the scalar product of vectors. So the dot product, right? What is E dot A? So that is magnitude of E, magnitude of A and the cos of the angle between them. So E dot A, so this is the dot product. Alright, so E A cos theta can also be written as the dot product of these two vectors. This is the vector, that is the electric field vector. Do you understand? And this is A vector. But what is A vector? So A is a scalar, right? A is the area of the surface. Then we have written this as a vector. So what is area vector? So area vector is defined like this. Or if you remember, what is area vector? So area vector is defined like this. So that is magnitude area only. So the area of the surface, that is the magnitude of the vector, but it also has the direction. What is the direction of area vector? So the direction of a surface is taken to be in the normal direction, right? Perpendicular direction. So n cap is the unit vector in the perpendicular direction to the surface, and that n cap is the direction of the area vector. So the magnitude is A, that multiplied by the unit vector in the perpendicular direction. So that is n cap. So this is also important for you to remember. The area vector is having magnitude, that area itself, and also has the direction in the perpendicular direction, normal vector. You understand? N cap is the normal vector to the surface. Alright, so that is area vector. So E vector dot A vector. So this is also taken as the definition of electric flux. Is that okay? Yes. Now see, this is very important to understand the difference here. Suppose there is a surface and there is electric field in this direction. So this is the electric field. Okay. Now this surface is not perpendicular to the electric field. This surface makes some angle, say theta, with the vertical. Okay. So the angle made by the surface with the vertical is taken to be theta. Now the normal to the surface. Okay. So we draw normal to the surface. So n cap. N cap is a normal to the surface. And that is the direction of the area vector. So that means area vector will also be in the same direction. Okay. So area vector is in the direction of the normal. Okay. So n cap and A vector, so both have the same direction. Now this theta is also the angle made by the normal vector with the electric field line. Do you understand? Because this angle is theta. This 90 minus theta, so this is again theta. So theta is the angle between the area vector and also the electric field. Do you understand? So EA cos theta. But what is this theta? So theta is the angle between this electric field and area vector. But remember, area vector means the vector which is in the normal direction. Do you understand? So not the surface. We are not finding angle made by the surface. Angle made by the normal vector. Do you understand? So the direction of this area is not along this line. So the direction of this surface is in the perpendicular direction. So that normal vector makes angle theta with the horizontal. That means theta with the electric field. That's why we use this formula E vector dot A vector. So EA cos theta, where theta is the angle between the normal vector to the surface and the electric field. Do you understand? So this is the formula which you have to remember. Now see, all these are important. It is not one point. You have to remember 4 points totally. See, first one, this is important because sometimes instead of using all these formulae, we simply use this idea because that is sometimes easier. Instead of using the formula, we simply use this idea, E multiplied by the projection of area in the perpendicular direction. Okay, so this is also formula. And sometimes this can be used when you know the angle theta between the area vector and the electric field. We can use this formula. Sometimes if you are given the vector form of the electric field and the area, so we can use this formula. So these 3 points you have to remember, and along with that you also have to remember this area vector. So what is area vector? So that area multiplied by the normal vector to the surface. Okay, so these 4 points you have to remember. Okay, all these are equally important. So these 4 points are important here. Do you understand? So that is the formula for electric flux in a more general case. Okay, so what is electric flux? So E multiplied by the area, the projected area in the perpendicular direction, or you can write it as EA cos theta, or you can write in the vector form E dot A vector, but that A vector is defined like this. Is that okay? Now as a particular case, if theta is 0, what is meant by theta 0? When theta is 0, it does not mean that the surface is parallel to the electric field. No. When theta is 0, so the surface will become perpendicular to the electric field. So that is the first case. Simply it will become EA cos 0, that is 1. So EA, that's all. E multiplied by area. So that is the first case we have written, when the electric field is perpendicular to the surface. Okay, now what if theta is 90 degrees? When theta is 90 degrees, that is when the surface becomes parallel to the electric field. So theta is 90 degrees, the surface becomes in this direction parallel to the electric field. So theta is 90 degrees. So cos 90 is 0. So that means the whole value becomes 0. So when the surface is parallel to the electric field, so the value becomes 0. Do you understand? Those two are the particular cases we have already done. So this is the most general case. Do you understand? So this is the formula, so that we are going to use for our questions. Alright. So electric flux is defined like this. Do you understand? So this formula you have to remember. Okay. So far we have only done electric flux through an open surface, like a flat surface. But this time we have a closed surface. We have to find the electric flux through a closed surface. Let us take a simple example, a cube. Okay, we have to find the electric flux through this cube due to this electric field in the horizontal direction. Okay, now let us find the electric flux. This is a combination of many surfaces. Looks like one surface, it's a combination of many phases, right? This cube has 6 phases. You have to find the electric flux through all the 6 phases. Do you understand? So let us find the electric flux separately and then add all these values. We'll get the total electric flux. Okay, yes. But there is one problem here. See, let us take this surface, okay, a flat surface like this. Now we have to find the area vector. So what is the area vector here? That is the area multiplied by the unit normal vector. But what is the unit normal vector here? But there are 2 unit normal vectors, right? One is in the upward direction, one is in the downward direction. Which one will you take? Will you take n cap or minus n cap? Both are unit normal vectors. Which one should you take? If you take one of them, say n cap, you may get the answer positive. If you get minus n cap, you may get the electric flux negative. But which one is correct? See, it doesn't matter. You can take any one of them. Even if you get negative values, you can leave the answer in terms of positive values only. Do you understand? It doesn't matter for an open surface, either n cap or minus n cap. So any one can be taken as the unit normal vector. No problem. But that is not the case with the closed surface. This time we have to define properly as to which normal vector to take. Do you understand? So it is very important here. See, for a closed surface, okay, you should always take the normal vector in the outward direction, not inward direction. Okay, so this is one point you have to remember. So the unit vector or the area vector to a surface is always outwards, right, for a closed surface. For an open surface, it doesn't really matter because there is no inward or outward. But here for a closed surface, the normal vector should always be taken in the outward direction. Do you understand? So that is one point which is important. So now let us find the electric flux through each of these surfaces. Do you understand? So let us first find the electric flux through the surface, say ABCD. Okay, this face. So ABCD. I'm writing like this. Okay, this is the flux through the surface ABCD. Okay, so that equals, let us use the formula EA cos theta. Okay, E multiplied by A multiplied by cos of the angle between the area vector and the electric field. So E is the electric field multiplied by the area multiplied by cos of the angle. But what is the angle? See, this area vector is in this direction, right? Negative direction, because outward vector. You understand? So remember, for a closed surface, you have to take normal vector in the outward direction. So normal vector or the area vector is in the outward direction, but the electric field is in the positive direction. Okay, electric field in this direction, but the normal vector is in the opposite direction. That means the angle between them is not 0 but 180 degrees. Do you understand? So not 0 because these two are in the opposite direction. So 180 degrees. So that is the electric flux through the surface ABCD. If you simplify this, we will get, okay, cos 180 degrees, that is minus 1. So this is E times A. So that is minus EA. So that's all. So that is the electric flux through the surface ABCD. Similarly, we will find the electric flux through the surface, say PQRS, okay, the opposite surface. So PQRS, so let us find that also. So electric flux to the surface PQRS. So that equals, so E, electric field E multiplied by the area, same area. So A multiplied by the cos of the angle between them. But this time you have to take the normal vector, again outward vector, the area vector is in the outward direction, that means positive direction. And the electric field is also in the positive direction, which means these two are parallel. So that means the angle between them is 0. Cos 0 is 1. So that means E times A. That's all. So this is the electric flux through the surface PQRS. Okay, done. So that means we understand that. So an incoming electric flux is always negative. Understand? So like this, incoming, which means the electric flux, the electric field enters the surface. In that case, the electric flux is negative. But outgoing electric flux is always positive. You understand here like this. You understand? So remember it this way. Now we have found the electric flux through these two surfaces. Now what is the electric flux through the other surfaces? What is the electric flux through the top surface? So that here the surface is parallel to the electric field, right? The surface is parallel to the electric field. In that case, the electric flux is 0. So directly we can write the answer. The electric flux through the top surface, so that is 0. Similarly, the bottom surface, that is also parallel to the electric field. So that is also the electric flux value 0. Similarly, the other two surfaces, front and back, they are also parallel to the electric field. That means the electric flux through the other surfaces. So directly I am writing the electric flux through the other surfaces equal to 0. Do you understand? So all the four surfaces have electric flux 0 and only these two surfaces, okay, so they have electric flux, this one, minus EA and plus EA. Now we want to find the total electric flux. So this implies the electric flux total. So that equals, so just add all these values, okay, so minus EA plus EA plus, so the other four surfaces 0, that's all. So that means this answer is 0. So electric flux, the total electric flux through the closed surface is 0. Okay.
Is it 0 for any closed surface?
Yes, actually it is true. Electric flux through a closed surface is 0. Do you understand? Not only for this cube, we have proved it for a cube, but for any closed surface, this electric flux is always 0 provided this electric field is uniform. Do you understand? This E is a constant value. For uniform electric field, the electric flux is 0 through a closed surface. Do you understand? If this E is a variable value, in that case, it need not be 0. Do you understand? So let us have this conclusion. The electric flux through a closed surface due to a uniform electric field is 0. Alright, it is very important. Uniform electric field, then only the electric flux through a closed surface is 0. What is uniform electric field? It is constant for all values. Okay, at any point in space, the electric field is same. Okay, it has a constant value, or E is a constant. If E is variable, at different points the electric field is different. In that case, it need not be 0. Do you understand? So these 2 points you have to remember. So electric flux through a closed surface is 0 in a uniform electric field. Is that okay? What if you have a non-uniform electric field? Will the electric flux be 0 in that case also? Let us check. Alright, so let us take the same example of a cube, but this time the electric field is not constant. It is dependent on the value of x. So it is given as 2x I cap. So the direction is fixed. It is I cap, which means the direction is always in the positive x direction. No problem. But the magnitude is 2x. That means it is dependent on the value of x. So as you move along the x-axis, the electric field intensity increases. Do you understand? So this is a non-uniform electric field. So let us find the electric flux due to this electric field. Okay. So let us first find the electric flux through the surface ABCD. Okay. So let us find. So the same thing we will find, but this time E is not constant. That's all. So what is the electric flux through the surface ABCD? So that equals, what is the electric field through the surface ABCD? See, on the surface ABCD, x value is 0. because it is on the yz plane. That means x value is 0 at any point on the surface. You understand? That means what is the electric field? Because electric field is 2x I cap, but x is 0, which means the electric field itself is 0. So that means the total value is 0. The electric flux is also 0. Do you understand? Electric field itself is 0, so electric flux is 0 obviously, because E multiplied by A, so E itself is 0. Okay, done. Now similarly, the other surface PQRS. So let us find the electric flux through the surface PQRS. On that surface also the electric field is constant on that surface, because that surface PQRS has x value, okay, A. So A is the value of x, A is the side, okay, length of the edge of the cube. That means A is fixed, okay, that means x value is A, that's all. So that is the value of x, A. So that means what is the electric field? 2x, that means 2A, that's all. So the electric field is 2A multiplied by the area, okay, multiplied by area. But what is the area of the surface? See, the edge length is A, that means A square. A square is the area of the square, so that means 2A multiplied by A square, so that means 2A cube. So that's all. So this is the flux through the surface PQRS. Now similarly, what is the flux through the other surfaces? So that is 0, right, just like this, because all the surfaces are parallel to the electric field. So that means that is 0, okay, just like this. So now the total electric flux here is, so what is the flux total? So that here equals, so 0 plus 0 plus 2A cube. So that is 2A cube, that's all. So that means it is not 0. So the total electric flux is not 0, because the electric field here is not uniform. You understand? So for a non-uniform electric field, so this value need not be 0. The total flux through a closed surface is not necessarily 0. That is the example. Okay. So this one point you have to remember: for a closed surface, the electric flux is 0 in a uniform electric field. Okay. Yep. Now we will find the electric flux due to a non-uniform electric field. See, in the last case also I gave you an example of an electric field which is not uniform, but that one was a very simple case. See, if not the whole region, the electric field was constant for a particular surface. On one surface, the electric field was a constant. Okay, but in the entire region it was not constant. For each surface, the electric field was constant. But here it is not even like that. See, it is a curved surface. So we have an electric field which is a variable. You have to find the electric flux due to this electric field through this surface. Do you understand? Okay. Now we can't find it directly, okay, because it is not a constant electric field. So what we have to do is we have to use the method of integration. Alright. So let us use the method of integration. So we cannot find the electric flux through this entire surface, because at different points on the surface the electric field is different. Okay, at various points on the surface the electric field is not a constant value, it has different values. So what we have to do is, let us consider a small portion, right, an elementary part. Okay, so this is an elemental area. Okay, through this area we will find the electric flux. Do you understand? So this small region has area dA. The entire area is A, so this is only that elemental portion, so we call it dA. So now we will find the electric flux through this area, because on this surface the electric field is constant, because this is a very small surface, right, very small area. So we can take the electric field to be a constant on this surface. Do you understand? So we will find the electric flux only through this area, and doing integration we will be able to get the electric flux through the entire surface. Alright, so let us find it. So we will only find the electric flux through the small area, so we denote that by d phi, okay, not phi, d phi, because only that small elemental portion. E vector dot the area vector. So area vector here is dA vector, right, because we are only finding electric flux through that small region. Okay, so that is area dA. So this is the formula for the electric flux through that surface, okay, that elemental portion. Now we have to find phi, which is the electric flux through the entire surface. So that is done by integration. Okay, so the phi value, which is after integration we get, so this is E vector dot product with the say A dA. That's all. So this is the formula for the electric flux due to a non-uniform electric field. Do you understand? So this dA depends on the question. Okay, you have to find dA. So depending upon what kind of surface is given in the question, so you will have to find dA. Do you understand? So E will be given in the question. So E is known. So dA you have to find. So that integration will give you the electric flux through surface due to a non-uniform electric field. Do you understand? So that is the formula you have to remember. Alright, now we'll take an example of a non-uniform electric field. Say E vector is 2x I cap. So that is similar to what we did previously, right? But the surface here is not parallel or perpendicular to the coordinate axis. It is a square, but that is making some angle theta with the horizontal. Do you understand? So that means at different points on the surface, the value of x is different. Do you understand? X is not constant at any point on the surface. So that means the electric field is also a variable. It is not a constant throughout the surface. At different points on the surface, the electric field will have different values. So we have to use this formula. Do you understand? So non-uniform electric field. So let us find the electric flux. So for this example, the electric flux d phi, only due to that small strip. Okay, we consider a small strip of length a. Okay, for that elemental portion only we will find the electric field, electric flux. So d phi equals that small strip that is in the shape of a rectangle. You understand? The length is a. A is the side of the square, so A is the length of the rectangle, and the thickness or the breadth is taken as dr. Okay, r is the distance from the origin, so that thickness is taken as dr. That means length multiplied by breadth. Okay, which means A multiplied by dr. So that is the area. I mean the magnitude of the area vector. Now we also need the angle. You understand? So what is the formula for d phi? So E vector dot dA vector, or E dA cos theta. Okay, E dA cos of the angle. So E. So E here is 2x. That's all. I'm taking the magnitude. E is 2x multiplied by the area. So area here is, so that is length multiplied by breadth. So the length here is A multiplied by the breadth is dr. So A dr multiplied by cos of the angle between the area vector and the electric field vector. So what is that angle? It is not theta. No, theta is the angle made by that plane with a horizontal. That means what is the angle made by the plane with the vertical? So that is 90 minus theta. Do you understand? That means the normal vector to the plane makes angle 90 minus theta with the horizontal. That means the angle between the area vector and the electric field line, that is not theta, it is 90 minus theta. So this is cos 90 minus theta. You understand? So that's all. So this is our d phi. You understand? But here there are variables. X is a variable, R is also a variable, but we want to make it in terms of one variable. Only then we can find the integration. Do you understand? So let us make it in terms of one variable, say R. Okay, can you write x in terms of R in that triangle? So what is the value of x? So it is a right angle triangle, right? So in that right angle triangle, so let us simplify this. So this value is 2 multiplied by A and cos 90 minus theta, so that is sin theta, multiplied by x dr. But what is x? So in that right angle triangle, okay, so this angle is theta, okay, this angle, right, alternate angle. So this angle is theta, so that value is r. Here, r is the hypotenuse, and also this x. So take the projection or take the trigonometric ratio, right? So if you take say cos theta is simply that x divided by r. So which means our x here is r cos theta. So that means, so the value of x can be written as r cos theta. So this is r cos theta d theta dr. So that's all. This is our d phi. Okay, so d phi. But what we want is phi. Let us do the integration. Okay, phi is found. Okay, let us do the integration. Okay, so 2a is a constant. Sin theta, cos theta are also constants. Remember, theta is a constant. Okay, theta is fixed. So sin theta, cos theta, a, all these are constants. Only variable is r, and also we have dr. So let us do the integration directly. So it is 2a sin theta cos theta can be taken out of the integration. So it is simply integration of r dr. That's it. So what is integration of r dr? But let us first write the limit of the integration. R starts from 0. Okay, so the minimum value of r is 0 and the maximum value is a, right? A is the side of the square. So 0 to a. So 0 to a, that's it. That's all. So this will give you the value. So 2a sin theta cos theta multiplied by, so this is r squared divided by 2. So if you substitute the limit, you get a squared divided by 2. So a squared divided by 2. So that is our required answer. So 2 gets cancelled. So which is a cube sin theta cos theta. So that's all. So this is our required answer. The electric flux due to this non-uniform electric field through that surface. Do you understand? So this is how we have to make use of this integration to find the electric flux due to a non-uniform electric field. Is that okay? Yep. Now let us write the unit of electric flux, right? Any physical quantity without unit makes no sense. So let us write the unit of electric flux. Alright, so we know the formula for electric flux. So electric flux is defined as this one. So E A cos theta. Okay, so this is the electric flux. Now E, that is the electric field. So that has unit. So the unit of electric field, so that is Newton per Coulomb. Alright, so that is the force divided by the charge. So Newton per Coulomb, so that is the unit of electric field, and area. So area's unit, so meter squared, and also cos theta. So cos theta has no unit, right? That's a pure number. So cos theta has no unit. So that means Newton per Coulomb meter squared. So that's all. So that is the unit of electric flux. So this is Newton meter squared Coulomb to the power minus 1. So that is the unit of electric flux. Okay. There is also another way to write the unit of electric flux. So that is voltmeter. Okay, so voltmeter. So that is another way to write the unit of electric flux. So this value Newton meter squared per Coulomb, so that value is also written as voltmeter. Alright, so this volt is the unit of electric potential. So that comes later on, so we don't need to do this in detail now. So just remember Newton meter squared per Coulomb, so that is also written as voltmeter sometimes, but both are equivalent. Do you understand? So this is the unit of electric flux. Okay. So here is the summary of all the concepts that we have done in electric flux. Alright, so you keep this list of all formulae for reference. So while we solve questions related to electric flux. Okay. The electric flux through the area bounded by the circle x squared plus y squared equals r squared due to the electric field E vector equals 6i cap plus 3j cap plus 4k cap. So here it is very simple. The electric field is given in the vector form. So we have to use the direct formula. So what is the flux here? So flux is simply the electric field vector multiplied by the area vector. You understand? So that is the formula for the electric flux in vector form. So that is okay, but what is area vector? So that is same as the area multiplied by the normal vector. Okay, the unit vector in the perpendicular direction. So tell me what is the electric field here? So that is 6i cap plus 2j cap plus 4k cap. So that is the electric field vector multiplied by area. So what is the area here? So that is a circle, right? So x squared plus y squared equals r squared. So that means it is a circle with radius r. So that has area. So pi r squared, that's all. So pi r squared. So that is the area, that is the magnitude of the area vector. Now what is n cap? N cap is the unit vector in the perpendicular direction. But this circle is in the xy plane. You understand? This circle is in the xy plane. So that means what is the perpendicular direction to the xy plane? So that has unit vector k cap, right? K cap is perpendicular to both I cap and j cap, right? K cap is the unit vector perpendicular to both x-axis and y-axis or the xy plane. Okay, so that means k cap. That's it. Simply multiply, you'll get the answer. So this is simply, so this is I cap dot k cap 0. So this is also 0. So k cap dot k cap. So that is 1. So this is 4 multiplied by pi r squared. So this is 4 pi r squared k cap dot k cap, that is 1. So that's all. So this is our required electric flux. Alright, it's very simple. So we are given an electric field vector and also the area vector we have to find. So that dot product will give you our required, alright, so electric flux. Okay. The dimensional formulae for the electric field and the flux are given by. Okay, so this is nothing, right? So we have to find the dimension of the electric field and also the electric flux. Alright, so very simple. Let us find the electric field. So what is the formula for the electric field? So that is force divided by the charge. Alright, so that is the electric field. So but what is force? Let us write everything in terms of our known quantities, right? The force equals, so mass times the acceleration, or if you know the dimension of the force, so we can directly also write, so force equals mass times the acceleration divided by q. So q does not have the fundamental unit, right? So that means you have to convert this q in terms of the electric current, right? So what is electric current? Charge per time, right? Unit time. So q here is simply this electric current, I multiplied by the time. Okay, so this relation you have to remember. So that's all. So let us write the unit of all these things, or dimension. So mass, so that has dimension m. Okay, so acceleration. So what is acceleration? So that has unit. What is acceleration? Meter per second square, right? So that has unit. So let us write the unit of this. So this has unit, or the dimension m, and then the acceleration is, so that is the meter per second square, right? So that means, so this is length second square, so second square per second square, this means this time to the power minus 2, and then this is I. Electric current has unit, the dimension I only, will denote this by I to the power minus 1. Okay, and then sometimes A is also used, A ampere, right? A is also used as a dimension of electric current, and time has the dimension T only, so T to the power minus 1. So if you do the simplification, so this will become, so the dimension is m L T to the power minus 3 and I to the power minus 1. So that's all. So this is the dimension of the electric field. Do you understand? So that is the dimension. Okay. So we'll also find the dimension of the electric flux, right? So electric flux can be written in terms of the electric field, right? So E multiplied by the area. Alright. We're not writing cos theta because that is dimensionless, right? So electric field multiplied by area, that much is enough. So what is electric field dimension? So that is what we found here. So mlt to the minus 3. So that you can simplify, substitute here. So mlt to the power minus 3 and I minus 1. This is the dimension of the electric field, and area. Area's dimension was length squared, right? Area L squared. That's all. So that is the answer. If you simplify, so this will become, so m L to the power 3 and T minus 3 I to the power minus 1. So that's all. So that is the dimension of the electric flux. Do you understand? So that is a very simple question. So we know the relation between the electric field or electric flux in terms of the known quantities, and then we can write the dimension. Okay, that's it. The electric flux through a square due to a point charge q placed at one of its vertices. So here we are given a point charge q which is placed at one of the corners of a square plate. So this point charge has some electric field, and we need to find the electric flux due to this electric field. Alright, so let us find it not using any formula. Directly we can answer this question. It's a very simple question. See, we know that roughly an electric flux is defined as the number of electric field lines passing through the surface, or the perpendicular components of the electric field lines passing through that surface. Now tell me, what is the direction of the electric field lines due to this point charge? See, these electric field lines are in the radially outward direction or radially inward direction if this is a negative charge. So these electric field lines are in the radial direction. Now you tell me, so do any of these electric field lines pass through that area? So these electric field lines are in the perpendicular direction, right? Perpendicular to the point charge. So none of these electric field lines pass through that area. If you take a different view, so these electric lines do not pass through that area. So what is the conclusion? No electric field lines pass through that area. So that means the total electric flux is 0. That's all. So that is the answer. Very simple question. See, so here in this case, this electric field lines do not pass through the area. So as these electric field lines do not pass through the area, so the total flux here is 0. So the flux due to the electric field due to this point charge through that surface is 0. So that's all. So that is the answer to the question. The electric flux through the curved surface of a closed hemisphere of radius r due to uniform electric field E perpendicular to the basis. Here we have a hemispherical shell, but it is a closed one. It has a curved surface and also flat surface. That is the base, right? It is a closed surface. Now we have a uniform electric field. Due to this electric field, we need to find the electric flux through these two surfaces. Can you tell me what is the total electric flux due to this electric field through the entire surface?
0, as it is a closed surface.
Yes, it is a uniform electric field and also it is a closed surface. So as we know, the electric flux through a closed surface due to a uniform electric field is 0. But the question here is to find the electric flux through these two surfaces separately. So we have to find the electric flux through this curved surface separately. So let us find it using two methods. Even though it is a very simple question, let's use two methods. So the first method is, as we know, the flux, the total flux is 0, alright, through these two surfaces. The total flux is 0, alright. What is meant by total flux? The flux through the curved surface and also the flux through the flat surface. These two values add up to 0. Do you understand? So that means the flux through the curved surface, let me write like this, plus the flux through the flat surface. Okay, so this total is 0. Okay, yes, that means the flux through the curved surface, so that equals negative of the flux through the flat surface. See, this one is very easy to find because the flat surface is already perpendicular to the electric field lines. So we know the formula. When the electric field lines are perpendicular to the surface, the electric flux is simply the electric field multiplied by the area. So that's all. So electric field multiplied by area. But area of that surface, so that is a circular disc, right? So the area here is pi r squared. That is the area of the circle, pi r squared. Yes, so this is the electric flux through the curved surface, minus E pi r squared. Similarly, we have the electric flux through the flat surface, so that has value positive E pi r squared. Alright, done. But we will also do this question by another method. Alright, so though it is a very simple question, so the other method may be required later on for other types of questions. See, or it can be done by this method. See, so we know that the electric flux is simply the electric field multiplied by area. But that is only when the electric field lines are perpendicular to the surface, like in the case of that base surface, right, the flat surface. So there the electric field lines are perpendicular to the surface, so simply electric field multiplied by area, that's all. But that is not the case with the curved surface, because the curved surface is not perpendicular to the electric field lines. But at one point this line is perpendicular, right? But at the other points this curved surface is not perpendicular to the electric field lines. So what we have to do is, so to find the electric flux through the curved surface, so that equals minus. Why minus? Because the surface, okay, the normal is pointing this direction, in the opposite direction to the direction of the electric field lines. So this is the direction of the electric field lines, okay, positive direction, but the normal to the surface is in the opposite direction, so minus, right? So theta is 180 degrees, so minus E, that is the electric flux multiplied by not the area, not simply E multiplied by area, right? So here, because this is not a perpendicular surface, what we have to do is E multiplied by the, not just the area, the projection of the area. Projection of area in the perpendicular direction. So we have to take the projection of the area in the perpendicular direction. What if you take the projection of the curved surface in the perpendicular direction? So that will be something like this. So it becomes a flat surface now, right? So what is this surface now? So this is a circular disc. Do you understand? So that hemisphere, if you project it in the perpendicular direction, now it looks like a flat surface. So that is a circular shape, right? So that is a circular disc. So that means the projection of the area is a circular disc. So what we do is minus E multiplied by, so what is the area of that circular disc? So that is same as the area of the base, right? So that is pi r squared, because the radiuses are, so E multiplied by pi r squared. So that's all. So this is the answer. So that's what we got here also. See, so this projection method is important. So the area is not perpendicular to the electric field lines, but we have to take the projection in the perpendicular direction. Alright, so this curved surface has projection, so that flat surface which is a circular disc, so that has area pi r squared simply multiplied by E, which is the electric field. So electric field multiplied by the projection of the area in the perpendicular direction, that will give you our required answer. Do you understand? So the answer to the question, the flux through the curved surface is this value, minus E pi r squared. Alright, yes. The electric flux to the curved surface of a hemisphere due to a point charge q placed at the center is. Here also we have a hemisphere, but unlike the last question, here the electric field is not uniform. The electric field lines are not parallel to each other like the last question. So here we have electric field due to a point charge Q placed at the center of the hemisphere. Alright, so here, so we have electric field due to the point charge, and due to which we have electric flux through the surface, and that's what we need to find. But this question is even easier than the last question because we don't need to take any projection or anything. So here simply, see, let us take one electric field line. So this electric field due to that charge Q. Okay, this electric field line is already perpendicular to the surface, isn't it? So this electric field is perpendicular to surface. Not only this line, you take any other electric field line, so that is also perpendicular to surface, because we know that the radial vector is perpendicular to the circle or a sphere. So this is a radial vector, so the electric field is always in the radially outward direction, so that is perpendicular to the surface. So any electric field line is perpendicular to the surface of the sphere. Do you understand? So that means it is a direct formula. What is the formula for electric flux when the surface is perpendicular to the electric field line? So the flux is simply E multiplied by the area. That's all. No need to take any projection or cos theta, nothing, because the angle theta is already known, right? So this surface is perpendicular to the electric field lines already. See, this E, the electric field, is already perpendicular to the surface. Or we can say that this E vector is parallel to the area vector. See, the area vector is parallel to the electric field lines, right? So when you say surface, so that is not area vector. So area vector is already normal to the surface, right? The surface is perpendicular to the electric field lines, or the area vector is parallel to the electric field lines. So both are same. So because this electric field is parallel to the area vector, or electric field is perpendicular to the surface, we can use the direct formula, the electric field multiplied by area. That's all. Even though it is a curved surface, this surface is always perpendicular to the electric field lines. Alright, yes. That means, what is electric field due to that point charge? So point charge is electric field, kq divided by r square, right? Kq divided by r. R is the distance, so that is the radius only. So kq divided by r square. So that is the electric field. Alright, this magnitude is constant because the distance is always fixed, r is fixed. So that means kq divided by r square. So that is the magnitude of the electric field multiplied by the area. Which area? The area of the entire hemisphere. Alright, so the entire surface has area. So 2 pi r square. Alright, hemisphere. This is the curved surface area of a hemisphere. So 2 pi r square. Area multiplied by the electric field will give you the direct value of the electric flux. Do you understand? So it is very simple here. So r squared gets cancelled. So this is 2 pi k q. Alright, so that's all. So this is the answer. But we will write the value of k in terms of epsilon 0. We know that k here is equal to 1 divided by 4 pi epsilon 0. So that if you substitute, so 1 by 4 pi epsilon. So pi gets cancelled. So which means simply q divided by 2 epsilon 0. So that's all. So this is the required electric flux through this curved surface. You understand? The hemisphere. So that's it. So that is the answer. Okay.
What if it was a full sphere?
See, this idea is same even for the entire sphere. So even for the whole sphere, the electric field is perpendicular to the surface. You understand? So the electric field lines are perpendicular to the surface of the whole sphere. So that means, so the same formula can be used here also. So instead of using the area of hemisphere, you can use the area of the entire sphere, right? What is curved surface area of a sphere? That is 4 pi r square. Do you understand? So that means the answer will be twice of this. So which is q divided by epsilon 0. So that is the electric flux through the entire sphere. So here we only need the electric flux through the hemisphere, which is q divided by 2 epsilon 0. Okay. The electric flux through a circular disk of radius r due to a charged semi-infinite rod of linear charge density lambda placed along its axis with one end at the center of the disk is. Here we have to find the electric flux through a circular disk. So the electric field here is due to a semi-infinite rod placed along the axis whose one end is at the center of the disk. So this semi-infinite rod has some electric field. Due to this electric field, we have some electric flux through the surface, and that electric flux is what we need to find. Alright, so here the electric field is not uniform. because we have the formula for the electric field due to a semi-infinite rod. So do you remember the formula? So for a semi-infinite rod like this, at a point above this end point, so we have electric field having two components. Okay, so one horizontal component in this direction, so that has magnitude k lambda divided by r. So this r is the distance. Similarly, it has a vertical component that also has the same magnitude k lambda divided by r. So the electric field has two components, the horizontal component and vertical component. So these two are same. Okay, the magnitudes are same. Do you understand? So this is the formula for the electric field due to a semi-infinite rod. Now due to this electric field, so we have to find the electric flux. But this value is not constant. So this is dependent on the value of r. Suppose you take a different point, you take different points on the disk. So that will have different electric fields because it is dependent on the value of r. At different points on the disk, we will have electric field different values. So it is not uniform. So what we have to do is, we have to use integration. Alright, so let us consider a small strip, okay, like a ring. So having some thickness dr, so having radius r. Okay, r is the radius of that circle and that thickness, right, that width. So that is taken as dr. Due to only this small elemental portion, we will find the electric flux. Then we'll have to use integration method to find the electric flux through the entire disk. Alright, so let us find the electric flux only through that small elemental portion. Okay, right. So that has value. So this is the flux. That is the flux only due to that small portion. So we denote it by d phi. Okay, after integration we'll get phi, which is the electric flux due to the entire disk. Alright, yes. So this has value, the electric field multiplied by area. Alright, so this electric field multiplied by the area. So what is the electric field formula? So that has formula this one, k lambda divided by r, because r is that radius that is fixed, the distance is fixed. So k lambda divided by r. So that is the electric field, k lambda divided by r. Okay, electric field is done, multiplied by the area. Alright, so what is the area?
You don't consider the vertical component?
See, this vertical component is not required. So this vertical component k lambda by r is not required. We only need the horizontal component. That horizontal component is only perpendicular to the surface. We want only the electric field component in the perpendicular direction. You understand? So the perpendicular direction has electric field only k lambda by r. So this vertical component, that vertical component is parallel to the surface. If an electric field is parallel to the surface, so the flux is 0. So due to this vertical component, there is no electric flux. So you can ignore this. You can only consider the perpendicular component, that is k lambda by r. So that's what we have written here. So k lambda by r is the only component that is in the perpendicular direction to the surface. So that is enough. So that multiplied by area. So what is the area of only that small portion? Okay, only that ring. So that has area. So what is the area? So we can consider that curved part as a rectangle, right? It has some length. What is the length of that rectangle? See, it is not like a rectangle. It is a curved part, right? So, but if you cut it across and stretch it, right? So that's what is the method we usually use, right? If you stretch it, that will be like a rectangle, and the length of the rectangle is the circumference of the circle, which is 2 pi r. So that is the length of the rectangle. And what is the height of the rectangle? So that is the breadth. So that is the thickness dr. So dr is the height and the length is 2 pi r. So what is the area? 2 pi r, length into breadth. So 2 pi r multiplied by dr, right? So that is simply 2 pi r, length multiplied by the breadth. So that is dr. You understand? So this is the required electric flux only due to that small elemental portion. Now we have to do integration to find the electric flux through the entire surface. Alright, so let us do the integration. This is d phi, but we want phi. Okay, phi equals, let us do the integration. So this r gets cancelled. So 2 pi k lambda. Alright, so integration of dr, that's all. But r ranges from 0 to capital R, right? Capital R is the radius of the disk. So that means 0. 0 is at the center. So 0 to capital R. So that is the range, the limit of this integration. So 0 to R. Alright, so that's it. So if you simplify, you get the answer. So this is 2 pi k lambda multiplied by, so that is simply R. Okay, so that is the answer. But we will write the value of k in terms of epsilon 0, right? K can be written as 1 divided by 4 pi epsilon 0. So that if you substitute here, so this pi gets cancelled. So that is, lambda r divided by 4 pi. So that means 2 epsilon 0. Do you understand? So that's all. So this is the electric flux through the entire disk due to the electric field due to that semi-infinite rod. Okay, so that's it. So that is the answer. The electric flux through an infinitely large plane due to a charge q at a distance r is. So here we will find the electric flux through an infinitely large plane. So the electric field here is due to a charge q placed at a distance r from the plane. So due to this charge q we have some electric field, and due to this electric field we have some electric flux through this surface. Alright, so let us find the electric flux. But here the electric field due to this charge q, is it perpendicular to the surface always? No, because the electric field due to the point charge is in the radially outward direction. Not all field lines are perpendicular to the surface. If you take one example, one of the electric field lines, so this is the electric field, but that is perpendicular to the surface, so no problem with that. But if you draw another electric field line, so that is not perpendicular to the surface, so we can't directly use the formula electric flux equals the electric field multiplied by area. So that can only be used when the surface is perpendicular to the electric field lines. Okay, so we can't use it, so we have to use the method that we have already used. So instead of using the area of the surface, we will take the area of the projection of this surface in the perpendicular direction. So what is the projection of this flat surface in the perpendicular direction to the field lines? See, observe this closely. See, if you take the projection of this flat surface in the perpendicular direction, so this plane is bent like this. Okay, if you bend the plane, so that will become perpendicular to the field lines. Do you understand? So this is the projected area. But what is the shape of this?
Semicircle.
No, it is not a semicircle. It is only a two-dimensional view. If you view this in 3 dimensions, that will be a hemisphere. Do you understand? Because from all directions we are bending this plane. So if the plane is bent from all directions, so that will form a 3-dimensional object, right? That is a hemisphere. Not a curve like this, it is a 3-dimensional shape, so that is a hemisphere. Do you understand? So the projected area is only the area of a hemisphere. Do you understand? So this is the formula we use. The electric flux here equals E. The electric field multiplied by not the area but the projected area. Okay, so projected area in the perpendicular direction. So the projected area in the perpendicular direction, which means the projection of the plane in the perpendicular direction, actually that is the area of hemisphere. So the hemisphere is the projection of this plane in the perpendicular direction. Okay, done. So what is the electric field? So now the electric field due to the charge q, so that has the formula kq divided by r squared. So kq divided by r squared. R is constant, fixed here, because it is a hemisphere. Any point on the sphere is at the same distance from the center, so that means R is fixed here, kq divided by r square. So that is the value of E, that is the electric field. Okay, now area of the hemisphere, so the curved surface area of the hemisphere, so that is 2 pi r square. That's all. So if you simplify this, we get the value, r squared gets cancelled, so it is 2 pi kq. That's it. Again, we will write this k in terms of epsilon 0. So 1 divided by 4 pi epsilon 0, 2 pi gets cancelled. So that is simply q divided by 2 epsilon 0. So that's all. So that is the flux due to that charge q through the surface, right? So the surface, the infinitely large plane, so that has surface same as the surface of a hemisphere as far as this electric flux is concerned. So this projected surface is the surface of a hemisphere. Do you understand? If you remember, we've already done a question with a hemisphere, so we got the same answer. So the electric flux through this infinitely large sheet, so that is same as the electric flux through the hemisphere, because the projected area in both the cases are same. Okay, so that's all. So this is the answer, q divided by 2 epsilon 0, that is the electric flux through the infinitely large plane. Okay. The electric flux through a circular disk of radius r due to a charge q at a distance x on its axis is. So here we have a circular disk. So we have to find the electric flux through this circular disk. So here the electric field is due to the charge q placed at a distance say x from the center of the disk. So we'll find the electric field and the electric flux due to that electric field. Alright, we will do this question by two methods. Alright, so the first method is a little complicated because we are going to use the method of integration. Alright, so that is a little complicated method. We also have a relatively easier method. So let us do both the methods, learn both the methods. Okay, so first let us use integration method. So obviously what you have to do, let's consider the small portion in the shape of a circular ring. So having radius r, having thickness dr. So let us find the flux only through this surface. Okay, only through that ring. So let us find it, and using integration we can find the electric flux through the entire disk. Alright, so let us find it. So first, for a change, we will use the vector method. Okay, instead of taking projection, so you can take the projection also. Alright, the projection of the electric field in the perpendicular direction, but I will use the vector form. Okay, so both are same. Let us use for a change the projection method. I mean the vector method. Okay, yes. So what do you do here? So the electric flux only through that small elemental region. So we call it d phi. Okay, yes. So that equals. So let us use the vector form of the electric flux. Okay, so we can take the projection also. I'm using vector form for a change. Okay, so electric field dot product with the area vector. Okay, so that area is only the area of that small portion, so we call it dA vector. Okay, so this is the formula for the electric flux in the vector form, E vector dot dA vector. So dA is the area of that small ring, right? So that area we will find multiplied by the electric field. So what is the electric field due to the charge q at that point? So at that point, any point on the ring is at a distance. So that is the right angle triangle. You can use Pythagoras theorem, right? The square root of r squared plus x squared. So that is the distance r. Do you understand? So that means this is kq divided by r squared. But r square here is what? The square root of x squared plus r squared squared. Do you understand? Kq divided by r squared. But r here is that distance. So that distance is, using Pythagoras theorem, the hypotenuse square root of x squared plus r squared. Do you understand? That is the electric field magnitude. But we want the vector. So that makes angle theta, right? So that electric field makes angle theta with the horizontal. So that means we can take the projection. So what is the vector along the horizontal? That is cos theta I cap. Okay, cos theta I cap. See, I am not taking the direction. I am taking this direction to be positive. It doesn't matter. Finally, the answer is positive or negative. Doesn't matter. For an open surface, the electric flux can be negative or positive. Doesn't matter. For closed surface, it makes a difference. So I am taking positive only. Cos theta I cap. So this direction I am taking I cap. Okay. Now similarly, the vertical projection. So that is sin theta j cap. This is the electric field, electric flux. Do you understand? In the vector form. This is the electric field vector. Okay, done. Now similarly, area vector. So what is area vector here? So dot product with the area vector. So what is the area vector? The area, the magnitude multiplied by the normal direction. Okay. So what is the area here? Tell me. So the area here is the area of that small strip, like we have done already. Alright, the length multiplied by breadth. But the length here is the 2 pi r, right, circumference, and the breadth here is the thickness, that is dr. So that area has magnitude 2 pi r dr. So that is the magnitude of the area. What is the direction of the area? So that direction, that means perpendicular to the surface. So that is in the x-axis direction, right? I cap or minus I cap, any one. So let me take I cap, say I cap. Understand? That's all. So this is the area vector. So this is the electric field vector. So dot product will give you the answer. Okay. So let us simplify this. So this will give you kq divided by, so this value is x squared plus r squared multiplied by cos theta I cap. So here I cap only. So I cap dot I cap. So that will become 1. So cos theta multiplied by and 2 pi r dr. Sin theta j cap dot product with I cap, so that is 0, right? J cap dot I cap, so that is 0. So that means this is the answer. If you had directly taken the projection instead of the vector form, you would have got the answer directly. Okay, but I have used the vector form. But anyway, you would have taken the direction directly, the projection in the horizontal direction, right? What is the perpendicular projection of E? Simply take the magnitude multiplied by cos theta. We could have written directly also, but I have used the vector form here. Okay, so now we have done. So this is d phi. Now we have to find phi by integration. That's all. So let us do the integration. So how will you do the integration here? So cos theta value we can write, okay, because it's a right angle triangle again. So cos theta can be written. So that will be, so kq. So cos theta here is simply, so in that right angle triangle, the value of cos theta is x, okay, the base x divided by the hypotenuse. Hypotenuse is square root of x squared plus r squared, but that is already there, x squared plus r squared square root, okay. Now this cos theta is simply x divided by the square root of x squared plus r squared. So that can be written as x, this is pi 2r divided by x squared plus r squared multiplied by square root of x squared plus r squared. So that can be written as x squared plus r squared to the power 3 by 2 dr. So that's it. So this is the value of d phi. So we want phi. So what do you do? Simply do the integration. That's all. So let me write here integration. So the integration for the variable r ranges from 0 to capital R. So that is the radius of the disk, right? 0 to capital R. So 0 to r. Let us do this integration to get our required answer. So how will you do this integration? So this integration is done by substitution method. So I'll just give you an idea. That's also t equal, let us take some new variable, t equal to x squared plus r squared. So that means the derivative dt equal, see x is a constant here, only r is a variable. You understand, r is the radius of that circle, that is a variable, but x is a constant, that distance. So dt is simply 2r dr. Okay, so if you do the substitution here, so 2r dr is already there, so which can be written as dt. So dt divided by t to the power 3 by 2. So that is simple integration, right? So dt divided by t to the power 3 by 2. I'm not doing that integration. I will write the value directly. So we can directly do it because dt divided by t to the power 3 by 2. So we can write it as t to the power minus 3 by 2 and do the integration. We'll get the answer. I'm writing the answer directly. So here it is 2 pi, okay, so 2 pi kq multiplied by, so this will give you 1 minus x divided by square root of x squared plus r squared. You understand? So that's all. So this is our required answer, the electric flux. But if you simplify this, so it will become, so we can write this value of k as 1 divided by 4 pi epsilon 0. So that will become, so this is so 4 pi epsilon, 4 pi, 2 pi gets cancelled. So this is q divided by 2 epsilon 0 multiplied by, so that value is 1 minus x by x squared plus r squared square root. Okay, so this is the electric flux through the surface, right, to the circular disc. Do you understand? So this is one of the methods of doing this question. Alright, we'll also do this question by another method. So this time we are going to use the method that we used in the last question. In the last question we had an infinitely large plane. That surface was not perpendicular to the electric field lines. So we did what? So we took the projection of that plane in the perpendicular direction. That became a hemisphere. So that hemisphere electric flux we found, right? So electric flux through the hemisphere we found. So that is same as the electric flux through the entire infinite plane. But here also we have a plane, flat surface, but that surface is not perpendicular to the electric field lines. We are going to take the projection. Do you understand? So let us take the projection. So we are going to bend it just like the last question. So if you bend this surface, okay, so if you bend it like this, so what will it become? So this also becomes a part of a circle, I mean the sphere. Do you understand? But the only difference is that it does not cover the entire hemispherical region, right? It only stops at some point, right? It doesn't become a hemisphere. So the only difference between the last question and this question is that the last question, that projected area was a perfect hemisphere, but this time it is not a complete hemisphere, only a part of it. So but the idea is almost same. So what we are going to do is, so this is the next method, so alternative method. Okay, so here the electric flux is simply the electric field multiplied by the projected area. Okay, same idea, the projected area. Okay, so what is the electric field here? So that is kq divided by x squared, not this one. So here we are finding the electric field due to the charge q at a distance x only, because any point on the sphere is at a distance x. So that means kq divided by x square, which is a constant here. So kq divided by x square, that is the electric field, okay, due to the charge q at any point on the surface. Okay, done. So this is electric field. multiplied by the projected area. So this projected area we have to find. So that is the problem. See, in the last case we had a hemisphere. So we know the formula for area of hemisphere. So that is 2 pi r squared. But this time, so we don't have a complete sphere or complete hemisphere. So that area we have to find. How will you do this? So we are going to use the method that we are already familiar with. So we have the formula, the solid angle. So what is the formula for solid angle? That is area divided by the square of the radius. Do you understand? So area by square of the radius. So this is the formula for the solid angle. That means what is area? Solid angle multiplied by the radius square. Do you understand? So that formula we are going to use to find the area. Do you understand? So this area is simply radius square. But the radius here is x. X is the radius of the sphere. So that is x squared multiplied by the solid angle. Do you understand? So solid angle. That's it. So this gets cancelled, x squared. So this is k cube multiplied by the solid angle. So what is the formula for solid angle? So we have written solid angle in terms of plane angle. So there is a formula, right? So 2 pi multiplied by 1 minus cos of the plane angle, cos theta. You understand? So 1 minus, so 2 pi multiplied by 1 minus cos theta, that is the formula for solid angle in terms of the plane angle theta. Okay, done. So let us simplify this. So this becomes, so k cube, again same thing, k 2 pi. So that will become, so k can be written as 1 divided by 4 pi epsilon 0. So that will become q divided by 2 epsilon 0 multiplied by 1 minus cos theta. Cos theta can be written from that triangle again. So that is simply x divided by square root of x squared plus r squared. Do you understand? So that's also, that is the answer. So same answer we got here also. So this is the answer, right? If you observe in this formula, if you substitute the value of r to be infinity, alright, suppose this value of r is taken to be infinity. So what will happen here? If this r is infinity, something by infinity, right? So this x finite value divided by infinity, so that will become 0. So this whole value becomes 0. So this is q divided by 2 epsilon 0. What is that? So that is the electric flux through a hemisphere. Do you understand? So that means if r is infinity, what is meant by r is infinity geometrically? So that means the radius of this disk is infinity. That means like infinitely large plane, like the last question. So infinitely large plane, so this r value becomes infinity. The answer will be q divided by 2 epsilon 0. So that was the last question. So that is a particular case. So last question what we did is a particular case where the radius of this disk becomes infinity. Do you understand? So the answer to this question here is simply q divided by 2 epsilon 0, 1 minus x by root x squared plus r squared. Okay. An infinitely long uniform line of charge per unit length lambda lies parallel to y-axis in the yz plane at z equal to square root of 3 times a by 2. If the magnitude of the flux of the electric field through the rectangular surface ABCD lying in the xy plane with center at origin is lambda L by n epsilon 0, then the value of n is. So here we have a rectangular plate having length L and breadth A. So this rectangular plate is lying along the xy plane. That means flat on the horizontal plane. So the center of this rectangle is at the origin. So this is the plate, okay, rectangular shape. So that is given. Now we have to find the electric flux through this rectangle, okay. But what is the electric field here? The electric field here is due to the linear charge distribution, like a long rod, okay, infinitely long rod, right, that is parallel to the y-axis at a distance root 3a by 2. So this is an infinite linear charge distribution. So that has some electric field, and due to this electric field we have electric flux through this surface, okay, this rectangle. So that electric flux is what we need to find, okay. So what we are going to do is the same method, right? So you take the projection of this rectangular plate in the perpendicular direction to the electric field lines. See, this is in 3 dimension. It's kind of difficult to comprehend the geometry of it. So let us view this from y-axis. Let us be on y-axis. So let's stand on y-axis. How will it look like? See, we are on y-axis now. So that means this y-axis here is perpendicular to the board, okay, and this is x-axis and z-axis, etc. Now, so where is our linear charge distribution? So that is parallel to y-axis, which means that is that small dot, okay, which is perpendicular to the board, right? So that small dot, so that is the linear charge distribution. That means that is a long rod. Now due to this long rod, we have electric field. So that electric field, is it perpendicular to the surface? Is it perpendicular to the surface, all the electric field lines? No. So at a point directly below that, so it will be perpendicular. Okay, but other points it is not perpendicular. So like we usually do, so we will take the projection of this surface in the perpendicular direction. That means we are going to bend this plane. Okay, if you bend this plane in the perpendicular direction, that will be something like this. So what is the shape of this?
A part of a sphere?
No, it is not a part of a sphere. See, it is not a circular disc that we are bending. See, it is a rectangular sheet. So when you bend a rectangular sheet like this, see, something like this, see, a rectangular sheet of paper. Now if you bend like this, so what will you get? If you bend it completely, so that will become a cylinder. You understand? So it is a cylinder, but it is not a complete cylinder, only a part of a cylinder. Okay, so this area is a part of a cylinder. You understand? So that the projected area is part of a cylinder, and that area should be multiplied by the electric field. Alright, that's all. So let us find the electric flux. So what is the electric flux here? So that equals, so E multiplied by that projected area. Okay, so that projected area is a cylinder. Okay, part of a cylinder. So I'll write like this, part of a cylinder. But what is E? So the electric field here is due to an infinitely long linear charge distribution. So that is a formula, right? Electric field due to an infinite rod. So that is formula 2k lambda divided by r. R is the distance. So that distance here is root 3a by 2. You understand? So that is the electric field multiplied by the cylinder area. But how to find the area of the cylinder? Okay, only this portion. We know the area of the entire cylinder, right? The curved surface area of a cylinder is 2 pi r multiplied by the height. Okay, 2 pi r multiplied by height. But that is the area of the entire cylinder, but it is only a part of the cylinder. So what we have to do is, so let us write the complete area, the entire area of the cylinder, that is 2 pi r. So 2 pi r, r here is root 3a by 2, again 2 pi r multiplied by the height. The height of the cylinder is that length, right? That is L. So 2 pi r L. But that is not our area. Okay, because so this is the area of the entire cylinder. We only want that portion. Okay, but that part makes what angle? That subtends angle 2 theta, right? Half of the angle is taken as theta. So 2 theta is the angle subtended by that part. But the entire cylinder will subtend what angle? That is 360 degrees, right? 2 pi. 2 pi is the angle subtended by the entire cylinder. But this is only a part of that. It subtends angle 2 theta. So only that part. So which means this ratio is simply this. So this is 2 theta divided by 2 pi. Do you understand? So this is the angle subtended by the portion which is required for us. This is the angle subtended by the entire cylinder. So the entire area is this much. So this is only the part of that area. Do you understand? So that's all. So this will give you the answer. That's all. Simplify, I'll get the answer. But how to find the angle theta? So it's a right angle triangle, right? It's a right angle triangle. In that right angle triangle, let us find the value of, say, tan theta. Tan theta. Opposite side. What is opposite side? So the opposite side is half of the breadth, right? So the total breadth is A. So half of that is A by 2 divided by that adjacent side, which is root 3a by 2. So tan theta here is, if you cancel this, 1 by root. So that will give you the value of theta. Okay, tan theta is 1 by root 3. So that means theta is 30 degrees or pi by 6. Okay, so that's all. So this is the value of theta, and that can be substituted here and simplify this. So what do you get? So 2k lambda. So this is root 3a by 2. So that gets cancelled. Root 3a by 2. 2 pi cancels with this, and 2 theta. So theta is pi by 6. So that will become pi by 3. So this 2 pi gets cancelled. Root 3a by 2 cancel. So this is L. You understand? So that's it. So this will become. Now again substitute the value of k. So that is 1 by 4 pi epsilon 0. So that will become, so 2 multiplied by, so this is 1 by 4 pi epsilon 0 lambda. So this is pi by 3 multiplied by L. Alright, so if you simplify this further, so this is 2 times 3. So that is 6, and this pi gets cancelled, and then lambda L. Lambda L divided by, this is 6 epsilon 0. So that's all. So this is the required electric flux. So that's also, that is the answer. So lambda L divided by 6 epsilon 0, that is the electric flux through that surface. Alright, so that rectangular plate. See, so what we did is simple. What we did here is electric flux is what? This electric field multiplied by the area. Which area? The area in the perpendicular direction. So here the electric field is not perpendicular to the surface. So what do? As usual, we found the projection of this area in the perpendicular direction, but that happens to be a part of a cylinder. So we are finding the area of that part of the cylinder, and that is the only calculation here. So we found the area, that's all. So electric field is known already. Electric field multiplied by the area of that part of the cylinder. To find that part of the cylinder, we use all this calculation. Okay, the entire area of the cylinder multiplied by that ratio, right, that part. Okay, so that's all. So that is the answer. You understand? So the answer to the question is simply lambda L by 6 epsilon 0. Okay. So we're done with our discussion on electric flux. The next class we will do Gauss law. Okay.